Hi, my name is Rebecca Hackett, and I did the script and the outline.
Hi, this is Jin Gao. For most of the time, I'm the group coordinator and I am in charge of the research part of this project.
Hi, my name is Stanley and I'm a sophomore studying data science at Purdue. I am responsible for taking care and creating the video for this presentation.
Hey everyone, my name is Alexander Corneon. I'm the editor of this video. I made the slides for the presentation and also talk in the conclusion part.
Today, we'll be speaking a bit about the solar neutrino problem, a hot-button issue in particle physics that plagued both experimentalists and theorists alike. The problem concerned the fact that there was a large discrepancy between the number of solar neutrinos that were predicted to reach Earth in comparison to the number that were actually detected. It took over 40 years and a re-examination of both the standard solar model and the standard model of particle physics to figure out why this was the case.
In terms of why we chose this particular topic, we think this is a particularly interesting and intuitively understood problem in the world of particle physics, which is part of why we selected it as a topic. While many issues within the sphere require significant background knowledge, the context of this topic doesn't require extensive explanation, and understanding the problem itself doesn't require that much background knowledge. In addition, we chose this topic due to its significance within the physics community. The solution involved adjusting the standard model, a theory that classifies all known elementary particles and 3 of the 4 total fundamental forces. This makes it the most basic and fundamental concept within the entirety of particle physics, according to the physicist Robert Alter's 2006 book, The Theory of Almost Everything, the Standard Model, the unsung triumph of modern physics. Any adjustment to the standard model then is a huge shift in the very framework of analysis for particle physics. Our video is targeted towards our classmates, so college students who have a scientific background or interest to some degree. We adapted the video by abbreviating discussions of the conflict between theorists and experimentalists, as it's not terribly relevant to our main topic, the actual problem itself and its resolution. In addition, we streamlined the progression slightly just by omitting minor development that doesn't contribute significantly on a large scale. This video could potentially be used to inform a lower division physics course about the basics of solar neutrino problems. In terms of communication principles, we made the language more accessible by defining any terms and jargon that students might not know, citing our sources in a way that flow naturally and nodded to the authority of those we cited. And also we used the assertion evidence model in our slides. On a whole, we wanted this video to be informative and interesting to as many people as possible who are anywhere on the spectrum of physics knowledge. So without any further ado, here is our video on the solar neutrino problem.
Have you ever felt lonely? Now, thanks to physics, now when you see your thumbnails, there are more than 65 million solar neutrinos that pass through your thumb each second. The solar neutrino problem was a hotly debated topic amongst particle physicists between experimentalists and theorists regarding the number of neutrinos predicted to be emitted from the sun and the number that were actually detected. But now, what is even solar neutrino and why is it important? The sun, as we may know, is powered by a nuclear fission called the proton-proton chain reaction, which converts proton into energy and subatomic particles, and solar neutrino is included in those subatomic particles. Now, the sun only produces one of a kind neutrino, which is called the electron neutrino, which is so small that it can pass right back out of the sun and straight to Earth. Neutrinos are a part of standard model, which is a classification system of the 4 fundamental forces. Now, according to physicist Robert Orter in his 2006 book called The Theory of Almost Everything, the Standard Model, the Unsung Triumph of Modern Physics, Prior to the 1960s, neutrinos hadn't been yet studied in much detail due to the facts that detectors weren't sensitive enough, you could say. So when the first detectors of sufficient sensitivity set out to measure the flux of neutrinos coming from the sun, it was a real revolutionary. The discrepancy and the detection of neutrino flux came into question in the homestick experiment run by Ray Davis and John N. Beckel in the late 1960s, which found that there was a significant discrepancy in the number of solar neutrinos predicted by the Beckel Standard Solar Model and the number of it being actually detected. Now, this is one of the examples of solar neutrino detection. It is in Japan and it is called the Super Kamiokande. Now, scientists initially took the approach of modeling the sun. At the very first, they thought that the fusion reactor in the center of the sun had briefly shut down. Therefore, they couldn't detect more solar neutrinos. But later, newer instruments and higher tech instruments proved that that was not the case. Now, as it would turn out, the solution was more elegant than either side could predict. It lay in the standard model in which there were three flavors of the neutrino: the electron neutrino, the muon neutrino, and the tau neutrino. The electron is the one that comes from the sun. All massless and invariant, meaning that one could not change its flavor. However, in 1968, Bruno Pontecorvo, an Italian and Soviet astrophysicist, conjectured in his paper Neutrino Experiments and the Problem of Conservation of Leptonic Charge that if neutrinos had mass, this flavor would change, or in a sense, leptonic oscillation would be possible. In 2001, his theory was confirmed by a publication by the Sudbury Neutrino Observatory, a collaboration that had an ultra-sensitive heavy water detector capable of detecting all three flavors of neutrino. Finally, not only did the observatory find the first clear evidence that solar neutrinos can change flavors, they also find that electron neutrinos constituted around 34% of the total neutrinos detected, which is in perfect agreement of the ratio implied by those experiments before. This modification of the standard model implies that the phenomena of the solar neutrino problem, which is the number of neutrino predicted to be emitted from the sun, was actually correct. It's just that they change flavor on their way to the earth. Something that we didn't possibly think given the time of understanding during the creation of the model itself. Thank you so much for watching.
Well, in the end, we're left with an elegant solution for an elegant problem. Neutrinos, which were thought to be massless, flavor invariant particles, and so the number of electron neutrinos that was emitted from the sun towards the Earth was actually overvalued by three times the actual value. After 40 years of discord between the theorists and experimentalists, they reached a resolution via the modification of the standard model of particle physics. This is because the massive nature of neutrinos allowed them to change flavor, which accounted for the discrepancy between the expected value and the actual value. This solar neutrino problem is the poster child for the age old saying, don't take anything for granted. Or as physicists say, don't take anything, even the standard model, for granted.